Welcome to this explainer. Today we are diving deep, literally, into the hidden mechanical properties of fluids. We're going to trace the incredible forces at play, starting from macroscopic pressure and buoyancy, all the way down to the microscopic, invisible world of surface tension. Here's our roadmap for today. We'll kick things off by defining fluids and pressure, move into fluids at rest and buoyancy, and then tackle the rules of fluid motion. After that, we'll look at Bernoulli in the real world, explore viscosity and internal friction, and wrap up with surface tension and capillarity. Let's get right into it.
Section 1. Defining fluids and pressure.
So what actually makes a fluid? Well, a fluid. It all comes down to the ability to flow. You see, both liquids and gases fit this bill perfectly because their atoms are just kind of randomly arranged. Unlike a rigid solid, a fluid simply can't withstand shearing stress for any real length of time. The very second you apply that stress, it just gives way, flows, and completely takes the shape of whatever container it's in. Now, you've got to notice the distinction between a general force and what we call thrust. Thrust is the total force a liquid exerts, but strictly perpendicular to a surface. Think about it. If you poke a hole in a plastic water bottle, the water shoots straight out, right? That is perpendicular thrust in action. And when we take that exact force and divide it by the area it's hitting, boom, we get pressure, which we measure in pascals. Moving on to Section 2, fluids at rest and buoyancy. Okay, this next concept is just brilliant. It's Pascal's law in action, which basically says that if you trap a liquid and apply pressure to it, that pressure is transmitted equally everywhere inside. Imagine applying just a tiny force to a small area. That creates a specific pressure, right? Well, because that exact same pressure travels completely undiminished to a much larger area, the resulting force is hugely multiplied. It's literally the magic behind a hydraulic lift. A tiny input force lifting a massive, full-sized car? Absolutely incredible.
Let's compare two clever measuring instruments. First, you have the simple mercury barometer. Its main job? To measure the sheer crushing weight of our entire atmosphere pushing down and forcing a column of liquid up a glass tube. On the other hand, we have the U-shaped manometer. This one uses fluid dynamics to measure the specific internal pressure of a trapped gas, and it does this simply by comparing the height difference of the liquid resting inside that U-tube. But what happens when you toss an object into that resting fluid? Well, Archimedes figured this out ages ago. His principle states that any body immersed in a fluid experiences an upward buoyant force that perfectly equals the weight of the fluid it displaces. Whether something sinks or floats comes entirely down to this delicate balance. If the displaced fluid weighs as much as or more than the object itself, it floats, which is exactly how we can build colossal steel ships that effortlessly cruise across the ocean. All right, Section 3, the rules of fluid motion.
When we set fluids into motion, they typically choose one of two paths. First, you have a steady, streamlined flow. Think of this like a highly organized parade of particles, where absolutely no two paths ever cross. Every single particle perfectly follows the one ahead of it. But, and here's the catch, if that liquid speeds up past its critical velocity, that beautiful order entirely breaks down into a chaotic, zigzagging, turbulent mess. Now, before we get into the heavy math of fluid motion, we really need to organize the energies we're dealing with. A steadily flowing liquid actually holds three distinct types of energy. First up is kinetic energy, which comes directly from its velocity and motion. Second is potential energy, derived from its height or position above the ground. And third, and this one is really unique to fluids, is pressure energy. This exists simply because a liquid under pressure has the built-in ability to do actual work. So if we take those three energy types and apply the universal law of conservation of energy, we get one of the absolute most famous principles in all of physics, Bernoulli's principle. It mathematically proves that in a steadily flowing ideal fluid, meaning one that's non-viscous and incompressible, the total sum of that pressure energy, potential energy, and kinetic energy always remains totally constant. It's a zero-sum game. If one goes up, another has to come down to balance the whole shebang. Section 4, Bernoulli in the real world. It's one thing to stare at a dense equation, but it's way more fun to see Bernoulli's principle solving everyday problems. Take the classic perfume atomizer. When you squeeze that rubber bulb, high-speed air rushes right over the top of the vertical tube. And remember, according to Bernoulli, high speed means low pressure. That sudden drop in pressure at the top creates a vacuum effect.
magically drawing the high-pressure liquid perfume up from the bottle where it collides with the air and sprays out as a fine mist.
And building on that exact same concept, we get to human flight. Consider the cross-section of an airplane wing, which we call an aerofoil. The top surface is highly curved. This means the air traveling over the top has a longer distance to cover, so it has to move much faster than the air underneath. Faster air above equals lower atmospheric pressure on top, while the slower air below creates higher pressure. That massive pressure difference pushes the wings straight up, generating the dynamic lift that allows incredibly heavy aircraft to just soar through the sky. Mind-blowing, right? Which brings us to Section 5, viscosity and internal friction. After looking at rapid motion and flight, let's slow things back down and look inward. You might naturally assume that liquid friction behaves just like solid friction, but there's actually a massive difference. Solid friction surprisingly ignores the contact area entirely. Viscous fluid drag, however, depends directly on both the area of the liquid layers in contact and their relative velocity gradient. Basically, the more fluid touching and the faster those layers slide past each other, the stronger that internal friction becomes.
This leads us perfectly into Stokes' law, which brilliantly models this drag force. Imagine a small marble dropping through a thick jar of honey. As it falls, its speed increases, which in turn ramps up the viscous drag, pulling back up on it. Stokes' law explains that eventually this upward dragging force perfectly balances out with the downward pull of gravity. The exact moment that happens, acceleration drops to zero, and the sphere reaches its absolute maximum constant speed, which we know as terminal velocity.
And finally, Section 6, surface tension and capillarity.
For our final stop today, we're zooming all the way in on the very top boundary of a liquid. Down at this microscopic level, there is a constant, invisible tug-of-war going on. On one side, you have cohesive forces fiercely pulling identical molecules together. On the flip side, you have adhesive forces trying to pull completely different substances together, kind of like how ink permanently bonds to paper. Ultimately, how a liquid behaves in a container just comes down to which of these two forces is currently winning the battle.
Depending on the victor of that microscopic tug-of-war, the liquid will actually form a very specific angle of contact with its container walls. If adhesion wins, the liquid clings to the glass and curves upwards, creating a concave meniscus with an acute angle. You see this every time you pour a glass of water. But if cohesion wins, like with a super dense fluid like pure mercury, it utterly refuses to wet the glass. It curves downward instead, creating a convex, obtuse meniscus. And all this surface tension leads directly to a phenomenon called capillarity, because the surface of the liquid acts kind of like a tightly stretched elastic membrane. Water inside a really narrow tube will literally pull itself up, seemingly defying gravity. It's wild to watch. But keep in mind, this elastic skin is quite fragile. You can easily wreck that surface tension just by cranking up the heat or adding solutes. Drop a little soap into that water, and you'll see that tight elastic surface instantly snap apart. Well, we have covered a massive amount of ground in this explainer today, haven't we? From macroscopic pressure multipliers lifting cars, all the way down to the microscopic tug-of-war happening on a single drop of water. With all of these mechanical properties finally decoded, I want to leave you with a question. The next time you spot a tiny water strider bug casually walking across a pond, relying entirely on surface tension, will you appreciate the incredible invisible fluid forces making that feat mechanically possible? Thanks so much for joining me today, and always keep an eye out for the amazing physics hidden right in plain sight.